I decided to tell you a story. It's not the best story, but it's a story I like, and it has a few chapters in it, and I warn you that at the beginning they may look a little disconnected from each other, but hopefully at the end they will. I mean, the story that I want to tell will actually take a sensible shape. So the first chapter is about generating functions and why we mathematicians like them, and why we should be interested in them. So this chapter is just through examples. There is no general principle. It's just a bunch of examples. So we start with this example of partitions. So if you have an integer, you can consider the number of partitions of this integer. Let's call it n. So we denote P1 of n, the number of partitions. What's a partition? It's a way of writing this integer as a sum of smaller non-negative integers. And it's well known that non-negative that these partitions are one-to-one correspondence with what one calls Young diagrams, which are depicted in blue. So, for example, for 0, there's just one partition, for 1 as well, because I can only write 1 as itself. And for 2, the integer 2, I have 2 partitions. I have 2 plus 0, or 1 plus 1. I have 3 partitions for the integer 3, because I have this one, or I have 1 plus 2, or 1 plus 1 plus 1. And you see the correspondence with Young diagrams. So I draw a vertical one for the full partition, and an horizontal one for the opposite, the totally spread partition. And then, for example, if we take 1 plus 2, so 1 is this little box here, and 2 is this taller column. Let's see 4. So 4, we have 5 partitions. So there is, as always, the full one. Or we have 1 plus 3, which corresponds to 1 plus 3, or 2 plus 2. So this 2 plus 1 plus 1, and finally the totally spread out partition. So we have 5. Let's maybe remember this 5. So I was saying that if you decide one day to compute the number of partitions of the integer 13, I promise you this is going to be a dark day for you. But if you are even crazier and want to try and compute how many partitions the number 2022 has, well, this is going to ruin your life. So the solution is a bit paradoxical. The solution is to put all these uncomputable numbers together in a generating function. So we introduce a parameter q, and we form the generating function. It's a formal sum of, with coefficients, the things we want to compute. So by the previous slide, we know that this generating function starts like this. So we computed up to this 5, which is the number of partitions of 4. Okay. So a few centuries ago, Euler proved that this generating function has this explicit form. So it's an infinite product, 1 minus q to the m inverse. And the proof is by, well, the modern proof is by contemplation. So let's compute together the coefficient of q to the 4th, so which we can confirm because we computed already. So how do we do it? Well, we expand this product in the following way. So for the first factor, we write, so with m equals 1, so we take the first factor, so we write it as 1 plus q to the 1 plus q to the 1 plus 1, and so on. And the next factor with m equals 2, we do the same, but instead of, you know, writing q to the 4th, we write q to the 2 plus 2, very silly, and so on. And now let's compute the coefficient of q to the 4th. Well, we see that there are a bunch of contributions which I tried to illustrate here. So for example, I pair 1 with q to the 4th, or I pair this q to the 1 plus 1 with the q square, and so on. So for example, this on top here I have q to the 2 plus 2, which pairs with 1 everywhere else in the other factors, and so on. And you see that there are exactly 5 contributions. So this is precisely the number of partitions of 4. And if you now that you have the formula and you believe it, well, you can just look at the right-hand side and extract the coefficient you're interested in. So if you do it for 13, you find 101. If you do it for 2022, you get this. And so I encourage you not to try and do this by hand, of course. So one can also go one dimension higher and consider plane partitions. So plane partitions are ways of stacking n boxes, so 3-dimensional boxes in the corner of a room. So this is a higher dimensional analog of the squares that we saw that define Young diagrams. This is a very concrete problem. You have n Amazon orders and you have to stack them somewhere, and you want to know in how many ways you can do this very concrete problem. So again, you define the generating function of these things, call it P2. So now the coefficients are the plane partition, the number of plane partitions, and this starts like this. So for one box, I have one way to stack it in a corner. For 2 boxes, I have these 3 ways, which I depicted in light blue. And McMahon in 1915 proved a similar formula for the number of plane partitions, or actually for the generating function, which is this formula. This right-hand side is today called the McMahon function. And so here's a recap of the formulas that we just saw, but there is a bad news, namely no such formula is known or expected to be provable in higher dimension, because you can imagine higher dimensional boxes and continue. There is a great deal of literature on higher dimensional plane partitions, but there's no generating function. Sorry, there is no formula as pleasant as these ones for the generating function. So this is where beauty stops. The second chapter is very short. It's an evergreen principle that I want to emphasize. That's true in mathematics, which is the following. So the principle is written down here, but I'll show you again with just an example. So in geometry, say you have a manifold, let's call it M, and you want to compute some invariants attached to this model, to this manifold. One numerical invariant that we are familiar with is the Euler characteristic. So what's the Euler characteristic? It's a sum of alternating sum of dimensions of the cohomology groups of our manifold, and that's an integer. Now, it's fun to compute Euler characteristics, but we should never forget that these numbers are just a shadow of something more sophisticated, something more refined. In this case, cohomology. You see, Euler characteristic is computed out of cohomology, and this is a more refined structure which carries symmetries which become invisible if we just focus on the number. For example, Poincare duality is a property of cohomology groups. So the lesson is whenever it's possible, do not forget, but rather focus on the most refined object available. And then the third chapter is about the most naive operation that exists in mathematics, which is counting. So I'll show you in just a slide what counting means in or has been meaning in enumerative geometry for the last, I don't know, 2 centuries. So let me start. I have divided this slide in 2. So let's start with the pink part, which is classical theory. So there is on this side the theoretical part, and on this side an example. So the first thing you have to start with is a question. So ask yourself something. For example, how many lines in a projective space make 4 general lines? This is a sensible enumerative question. Then you find a moduli space, which is a space, if you want, a manifold, which parameterizes the objects you're interested in. In this case, the question asks about lines, so it is natural to take M to be the Grassmannian, because it's a parameter space for lines in projective space. And then you look back to your question and you say, okay, what is my question asking? So what are the conditions I have to impose? And in this case, in this example, the conditions I have to impose on the full set of lines is they have to meet 4 general lines. So I focus on sub-manifolds of my moduli space, which parameterize, which describe these incidence conditions. So I took, for example, this, in this case, the set of lines which meet one of my general lines. And then the crucial part is to then use intersection theory to count the intersection between these submanifolds. And so the intersection theory tells you that the answer you want is the degree of a product of the cycles associated to these submanifolds. And if you're interested, in this case, the answer is 2. So here, this product symbol is the product in the cohomology ring of the Grassmannian. So here we are intersecting 4 divisors for codimension 1 subvarieties inside a 4-dimensional space. Okay, this for the classical story. Now the modern story, which started around 25 years ago, is completely different. First of all, you have no question. You start with a moduli space you like, and usually the problem is that the moduli space you like does not allow you to compute numbers of this form directly, because the reason why we can compute this is because in this example M is the Grassmannian, so it's a smooth compact manifold. But in general, the moduli spaces we are interested in are way more complicated. So the second step is to hope that the space we want to study is nice enough. And nice enough means several technical things, but one is that we should be able to say what the expected dimension is, for example. And also, we would like to say that maybe if the space is bad and so it doesn't have an actual fundamental class, maybe there is a substitute for the fundamental class, which I denote here by nvir. So vir stands for virtual. So the fundamental class that it would have if it were nice enough, as in the classical setup. And then the third step is to just compute everything. So you take all cohomology classes that you can think of, whose degrees, whose codimensions add up to the virtual dimension. So this expected dimension that we have, and then we integrate the product of those against the virtual cycle, and that gives us an integer. And now the general principle says that we should compute generating function of these numbers and find some nice structure, even though the moduli space was hard to understand. So you see, it's completely different. Before we used to have a concrete problem to solve, and now the problem is not there anymore. We care about the spaces, and of course we are free at the end to add one more item and interpret the numbers we obtained, but that's not very common. Okay, so now I want to give you an example of counting and an example of this virtual dimension or expected dimension, because I understand it may look a bit abstract, but I will make it clear in a second. So counting critical loci, this is next chapter. So what's a critical locus? So say you have it depends on your favorite category. You can work with smooth algebraic varieties or complex manifolds. So in the first case, you look at the regular function, or in the latter case, you look at holomorphic function on them. And once you have such a function, well, you have the exact one form df. So this section of the cotangent bundle, and you can look at its zero locus. Well, the zero locus of this exact one form is called a critical locus. It's canonically attached to the pair UF. So my point is that this is the prototypical example of something which has virtual dimension 0. So something that we should be able to count. And why it's virtual dimension 0? Well, here is a very naive picture, but imagine the cotangent bundle. So this is a manifold of dimension twice the dimension of the manifold U we started with. So what is the f equal 0? Well, we are intersecting 0. So the 0 section, which is a copy of U, with the section df, which is another copy of U somehow. And so since we are intersecting two things of complementary codimension, we expect the dimension to be 0. However, I tried here to draw a pathological but very frequent behavior, namely the fact that the intersection is not transverse. This happens all the time. And in the algebraic category, you cannot deform your f to achieve a transverse intersection in general. So this really is a problem, and it's different with the smooth category. But still, you can say that the virtual dimension is 0. This is an example. Now, the importance of critical loci stands in the following. So once you have a critical locus, you can, of course, so you always have cohomology, but in fact, there is a more interesting coefficient system for cohomology. So this is the sheaf of vanishing cycles. It's a complex of constructible sheaves on the critical locus itself, and it lies in a certain heart, the heart of perverse sheaves. It doesn't really matter. The definition is not important. I'm not giving it. What you have to think of is just that instead of, so you rewrite the formula for the Euler characteristic, but instead of putting Q here, you take this weird coefficient system, which I claim is canonically attached to the pair UF. So this has some meaning, and once you do this, and you just rewrite formally the formula for the Euler characteristic, you get something new. It's a new number, and we call it the virtual Euler characteristic. So this is an invariant that one may want to study. It's an integer invariant. So one possible motivation for this virtual Euler characteristic is a result of Berend from 2009. So here I'm stating just a very small consequence of Berend's theorem, but one consequence is that when your critical locus is compact, so you can integrate cycles. Well, you have first of all this virtual fundamental class, which is of degree 0 because the virtual dimension is 0. So you just take the degree of this virtual class, and this number, which is the one you would like to compute according to this principle. So here you just you don't have this. It's the easiest equation. You have no insertions. Just put one here. This is what you want. And what I'm saying is that by Berend's theorem, this thing agrees with the virtual Euler characteristic. However, the right-hand side only makes sense if Z, the critical locus, is compact, but the left-hand side always makes sense. And in what follows, we are going to focus on the situation where Z is non-compact. So we will not have this, we will study this instead. So this result was really a breakthrough in enumerative geometry. This is a very important result. So now I will introduce a more geometric chapter. This would be about modular space, which is very classical in enumerative geometry. It's many years old, like 60 or 70 years old. It was introduced by Grothendieck. It's a quad scheme. And we will focus on a very special type of quad schemes. So let's see. I will just give you a very explicit description of the quad scheme. I will not give the precise definition, but an equivalent formulation. So here's the data we start with. So we fix 3 integers. First integers is positive. It's a rank. It will take the role of rank, I will say. In what sense? Then we have an ambient space dimension and a number of points. Now all these 3 things will make sense in a second. So let's take the polynomial ring in D variables with complex coefficients. So this we can see as the coordinate ring, or the ring of regular functions on a affine space. Okay, so this is for the D, dimension of the ambient space. And now we consider, so we do this. We take R copies of this polynomial ring, and we consider all surjections which are surjections of RD modules, where the quotient is a finite length module supported on points. So this means that the dimension of the quotient as a over the polynomial ring, sorry, over the complex numbers is finite. And this number, this dimension, is n. So in other words, if you see it geometrically, it means that so T corresponds to a sheaf supported on n points. Okay, so this is all very classical. For example, if you take R equals 1, what you get is what's called the Hilbert scheme of endpoints. This parameterizes the subschemes, the subvarieties consisting of endpoints. So in general, you have this is your affine space, and the general point is a collection of endpoints on your affine space. And this guy, which we call just to shorten a bit the notation QRND, is the higher rank generalization. So this R here has this role. It appears here. Okay. So this is a classical moduli space in algebraic geometry. But let's see more concretely how it is built, or how can one describe it. So let's pick a point in this space. So it's we take a surjection as I just described, and let's analyze what it means to be such a surjection. So first of all, so let's see the definition here. Let's start from this condition. So here we have a vector space over the complex numbers of dimension n. So let's pick this first. So we fix an n-dimensional vector space. But we required that this should be also an RD module, a module over the polynomial ring, because we were looking at RD linear surjections. So we have to give this vector space a module structure. What does it mean to give a module structure? It means to give a ring homomorphism from the base ring to the endomorphisms of our wannabe module. And what is that? Well, RD is a polynomial ring, so I have to give you for every indeterminate an element here of this endomorphism ring. So I have to give you D matrices. Now, the D matrices correspond to multiplication by the variables x1 to xd. And so, since the polynomial ring is commutative, these matrices are required to be pairwise commuting. But I encourage you to forget this condition for a second. So I wrote it in red. They have to commute with one another, but let's forget about it. We pick it up later. So now we have to take care of the map. So we have to construct a map and make it surjective. So the map is easy. We have to just take the coordinate vectors here, like 1, 0, 0, 0 up to 0, 0, 0, 1, and send them somewhere. So we have to pick our vectors. This defines the map. And then we have to impose surjectivity. Okay, but what is surjectivity? Well, the polynomial ring is spanned by the monomials. So Rd is this ring, right? So it's spanned by monomials in x1 to xd. But I just assigned the matrices to x1 to xd, and so I must declare that monomials in these matrices applied to these image vectors span the whole of V. And this is this condition that I wrote here. So I take all the monomials in my matrices, I apply them to my R vectors, and this should be a vector space of maximal dimension, so equal to V. Okay, this is the data. Now I construct a manifold which encodes all these data except this commutativity, which I asked you to forget. So let's do it. We have D matrices, R vectors, and the spanning condition, this condition here. However, one thing to remember is that we chose a vector space, okay? But here there was just a condition that the dimension is equal to n. So we have to forget about this choice. And so we mod out by GLV. Okay. So an observation, not too hard to prove, is that this is a complex manifold. And it has the dimension that you expect. So it's d minus 1 times n square plus Rn. D minus 1 n square, because here I have d matrices. So it's d times n square, because the matrices are n by n. But I remove 1 because of this quotient. And then I have R vectors. So dimension is easy because we have d matrices n by n, so it's dn square, but I remove 1 n square because of this quotient, and then I have R times n because I have R vectors. And I can decide that I want to look inside this space, the locus where the matrices commute. And this is the quote scheme. So we don't need the general definition. This is a possible definition. It's very concrete. Now, we focus for the rest of this talk on the case where the dimension is 3. So we have 3 variables. This is the most special case. It is special because if we start from this variety, so I didn't say why I called it that. So this NC stands for non-commutative, just because it's a quote scheme, but we don't require the matrices to commute. So when it becomes commutative, we just call it that, Q. Okay. So on this space, before imposing commutativity, we have a function which takes, so it has now 3 matrices, R vectors. It does nothing to the vectors, and it takes the trace of first matrix times the commutator of the other 2. And what is special about dimension 3 is that the quote scheme, which sits inside as the locus where the 3 matrices commute, coincides with the critical locus of this function. This is something I always find mind-blowing. It's proved, it was proved by Balázs-Szendroy for R equals 1, and his proof got improved by Benches and myself for every rank. But the idea is really to contemplate very intensely this function and see that its derivatives, so the vanishing locus of its derivatives precisely cut out these conditions that the matrices commute. So we conclude that the quote scheme is a critical locus because it is of this form and because this is a complex manifold. And now one can wonder, okay, it's a critical locus, then I run the machinery of cohomology of vanishing cycles, so I can compute the virtual Euler characteristic, but I don't want to compute one because otherwise life is a mess. I want to compute the generating function. And the upshot is that this generating function is a function we already met, the McMahon function. But it's assigned, so I don't have the usual variable. I have -1 to the rank times the variable, and the whole thing is raised to the power r. So remember, this P2 is the generating function of plane partitions. And these numbers, these virtual Euler characteristics, are called the rank r degree 0 Donaldson-Thomas invariants of affine space. So there is not much to explain here. So the 3 is the dimension of the ambient space. The r is the rank, it's arbitrary, and degree 0 refers to the fact that we are looking at zero-dimensional quotients. So this is the enumerative formula that we get. And it was proved by Berend and Fantecchi for r equals 1, and again improved by my collaborator and myself in general. So for arbitrary rank. Okay, so much for the numbers. But so in case we are not interested in just the numbers, but in exploring more refined structures, such as so the analogs of, if you want, Poincare duality, so the symmetries that we are losing, well, I claim that these symmetries are hidden in this description. So this description is the starting point of our ability to refine these numbers. And there are at least, there are many refinements, but for the sake of this talk, I will only describe 2. So one is motivic refinement, and another one is cohomological refinement. So we study the cohomology of the sheaf of vanishing cycles. We start with the motivic one by describing a motivic analog of this sheaf. Okay, so here we go. So a classical object of study in algebraic geometry is the Grothendieck ring of varieties. So this is defined as follows. You take all isomorphism classes of complex varieties, you take the free abelian group on them, and you quotient out the seesaw relations. The seesaw relation says that whenever you have a variety and a closed subvariety, then the class of the bigger one is the class of the closed subspace plus the class of the complement. So this quotient is denoted K0 bar, Grothendieck ring of varieties. It can be described by a universal property. I just wrote it here very informally. So you have this association. This is not really a function. It's because this is a category and this is a ring. But you can send a variety to its motive, which is its class in K0 bar. And the thing is that whenever you have an invariant of algebraic varieties which behaves like the Euler characteristic, namely it's 0 on the empty set, it's 1 on the point, it's multiplicative, and it respects the seesaw relations, then this invariant, which I denoted by E, factors uniquely through a ring map from the K0 bar ring. So in this ring, there is a particular class, which is the Lefschetz motive. It's a class of A1, the affine line. And one can add, so one can slightly enlarge this ring and make it even more mysterious by adding the inverse of a square root of L. And this is where the refinements of the virtual Euler characteristics that we studied live. Now, the upshot is that if you have a critical locus, so you start with a pair, complex manifold, and holomorphic function, you take the f equals 0. Now, a very powerful construction, very important, by Deneuve and Leuser, is a construction of a certain class, which is called the motivic vanishing cycles, which is the analog of the sheaf of vanishing cycles that we saw earlier, times this shift by a power of the Lefschetz motive. And this is called MF, to stand for Milnor fiber. It's some class in M, in this motivic ring, which is canonically attached to the pair UF. So this is something we have. It's given to us, thanks to Deneuve and Leuser. So what is it for? So its crucial property is that if you now extend the Euler characteristic, which is a homomorphism, so as I'm using here the universal property, of course, the Euler characteristic behaves like the Euler characteristic, so we have a map like this. And if we extend it to the full motivic ring, so we add this this element, and we declare that it has Euler characteristic -1, then the Euler characteristic of this Milnor fiber is equal to the virtual Euler characteristic that we wanted to study. So this class is a motivic refinement of this number. Okay, so now we go back to our quote scheme, which we realized as a critical locus. So we have an ambient space U and the function f, the function we saw before, the trace function. So we can construct this Milnor fiber attached to this pair, and we call it dt motivic. So motivic dt invariant. By what we just saw, it has the property that its Euler characteristic computes the virtual Euler characteristic. And this, so it's just a bit of terminology. So one may want to call this the motivic Donaldson-Thomas invariant of rank R, of course. So, usual principle, we form the generating function, and we hope we are able to compute it. So now the coefficients are not integers anymore, they lie in this complicated ring of motives. And one of the most important and beautiful calculations in the subject is due to Beren, Bryan, and Sendroy. They proved for rank 1 that the generating function has this form. This is a very beautiful formula. So it's entirely in terms of the Lefschetz motive. So it's a full calculation. But we also have the generating function for higher rank, because at some point we extended the critical locus description, and so we have it for all ranks. And the answer is given by this formula. So it's it can be computed. We did it with collaborators via motivic wall crossing using Hilbert representations, dimensional reduction, and a bunch of other techniques. And so we have a full control on the motivic dt invariants of higher rank as well. But so of course, it's not a big improvement, but an interesting feature is that once you have this formula, you can play with it a little bit and prove that it can be also rewritten as a product of R rank 1 motivic generating functions with not the usual variables, but just a shift. So this is meaningful in more than one way. So it has been believed in string theory, for example, that these kind of counts in higher rank are totally governed by rank 1, by the rank 1 counts, and this is this formula confirms it. And this is not the only the only case in which it happens. I know many more examples where this phenomenon occurs. So yeah, rank R totally governed by rank 1. This is actually the result I like most. And then we have the cohomological refinement. So it's just as I was saying, instead of looking at motivic vanishing cycles, we go back to the cohomology of the sheaf of vanishing cycles, and we study this cohomology, just as instead of studying Euler characteristic, we study the cohomology of a space. Except in this case, we have much more structure. So because the sheaf of vanishing cycles was a perverse sheaf, the cohomology, which is now a graded vector space, it has what's called a mixed Hodge structure, and it is there is a very powerful result of Ben-Davison, which can be used to prove that this Hodge structure is pure of Tate type. So this means that it's essentially decomposed as a sum of shifts of the Tate motive, where the Tate motive is this class L, the cohomology of A1. So the cohomological analog of the Lefschetz motive. So for this, you need the theorem by Ben and a description which I didn't give you of the quad scheme in terms of quiver representations. But the result essentially follows from Davison's theorem. Okay, so last invariant for today is the Hodge series. So if you have a cohomologically graded mixed Hodge structure, such as this thing, well, you have two filtration, one increasing and one decreasing. So you can build a power series where there are a bunch of variables x, y, z. So there is a cohomological degree A, which is taken care of by the first variables, and then the other two variables encode the various pieces of the two filtrations. So you have such a generating function. Sorry, power series H. Okay, so now we have such a thing for every quad scheme. And so we can form the generating function of these power series. So we take the sum over all n, q to the n, and we put here all these, all these power series. And in order to obtain a nicer formula, we shift slightly. And what we get is something very similar to the motivic generating function. We obtain this. So this was a theorem of Ben-Davison for rank 1, which was quite easy to generalize to higher rank. Okay, so this is a formula for the Hodge series. And I conclude by saying that there are many more refinements of the virtual Euler characteristic. For example, I think the most powerful one is the K-Theoretic refinement, which uses structures of the quad scheme which we haven't seen. But I wanted to tell you a story, so I just told you about the critical structure, which is actually where it all begins. But if you're interested, there are more refinements. And the K-theoretic one is certainly the most sophisticated, and it leads to very interesting formulas, which have been conjectured in string theory and later proved mathematically. So it's a very interesting area. And with this, I thank you for your patience and for staying with me for this hour, and sorry very much for the technical troubles.